Hello there, people. Since we've learned the first derivative test, I thought it'd be useful to learn the second derivative test. And the second derivative test in calculus really doesn't talk about where a graph's increasing or decreasing anymore. It talks about the curve. We're not going to discuss too much about the curvature except to say that it is concave up or concave down, and that the points where that changes are pretty interesting. So, the quick calculus definition. Actually, forget that. Let's go to the basic definition. Look towards the bottom here. Something's concave up or concave down depending upon how it curves. If the curve kind of opens up, like the little cave here, opens up going down, that's concave down. Likewise for it opening up. Technically, I know you could say this is concave right or concave left, but we don't do that. Someone a long time ago just decided we're going to use up and down as our designation, and it works really well. So let's stick with that. Now, the point where it changes concavity from down to up or from up to down is called an inflection point. So an inflection point is where a concavity changes. This is where I want to go to the calculus definition of concavity. Because if I showed these pictures to a third grader, they would be able to look at them and say, yeah, I can see where it curves down or curves up. They can identify that. But here's what it really means. Something is concave up if the slopes, the instantaneous rates of change, the slopes of the tangent lines are increasing. Okay, so if you look at the example, I keep running over this little pointer here. Every slope on there is positive, but you'll notice they get steeper and steeper, so more and more positive. Likewise, on this other example, where every single slope of the tangent line is negative, they're becoming bigger values. This might be a slope of -2, and then a slope of -1, and then a slope of -1/2. So while the slopes are negative, they are increasing. The same thing applies for concave down intervals. The slopes are decreasing. And here's why. If you want to find out, remember how the slope is the first derivative? If you want to see if a slope is increasing or decreasing, take its derivative. So the derivative of the slope is the second derivative. Where it's positive, the slope is increasing. Where it's negative or less than 0, the slope's decreasing. So that's a really easy way of finding concavity. We'll just do the second derivative. We'll test it. We'll make a sign chart. It'll be great. I do want to point some things out on this graph right here in the middle from A to H. Some of these points are inflection points. Which ones? Well, it's really quite simple. Point B, the graph changes from concave up to concave down. So point B is an inflection point. Point G is also an inflection point. It goes from concave down, and then at G it changes and goes to concave up. So B and G are inflection points. What about point E, you may ask? Did the concavity change? It's concave down all the way up to point E. Then you have this little cusp, and then it's concave down again. If the concavity doesn't change, E is not an inflection point. And that's where this last statement comes in. Just because your second derivative equals 0 or doesn't exist, doesn't mean it has to be an inflection point. The second derivative at the point E here is undefined, but it's not an inflection point. However, we do know every single inflection point will have a second derivative that is either 0 or does not exist. So you have to make sure it's in the right order. We'll make a sign chart to test it, and I will show you how to do that in the next video.